All right. So we do remember where we left off, yes? First, where we left off is exam is due today, and it's due at midnight today, right? Not yesterday midnight, but today midnight at the end of the 27th. What happens if you do not deliver the exam to me at midnight? What do you think happens? No, you deliver the exam the next day, or maybe the day afterwards. That's what, right? That's what happens, hopefully, right? And if not, then I suppose, we do Bayesian statistics, right? Either you deliver the exam today by midnight, or tomorrow by midnight, or the day after by midnight, and so on into infinity. Good? Is there a penalty? Well, you feel ashamed that you didn't deliver this exam on time, as you had a lot of time, really, for my class. Really, I gave you 2 weeks to do this one exam. That if you practice for the actuarials, you have to do many questions of that type in like 5 minutes, right? 5 to 10 minutes. It's not an easy exam because of the speed. Right? I actually yesterday couldn't fall asleep because, my God, I thought of such interesting questions for your next exam. I just do not know if I can fit all of them into just an exam of 10 questions. Well, 12 questions. I have extra credit. Yes. So guys, turn on your cameras so that what is it? Interesting. Well, interesting, hopefully, because you just you cannot fall asleep because it just bothers you so much that such a question that just even if you solve it, it still kind of runs in your head as you are so interested. What? Yes. Good. So turn on your cameras, guys, and today we begin another very important lecture. What do you mean, the subject of the email? I don't follow the question. What should you send when you submit my exam? Say just exam 1 and title the file. It should be one PDF file. You understand? One. I don't want to see many pictures of it. Ideally, it's with the body of the exam. So I see the question and then I see your answer. Yes, and I like it to be in order, please. Like 1, 2, 3, 4. I just like that type of order. Like we do in Kafka protocol. Right? If you just think about it, guys, I'm so nice. If you went to Germany, do you know what would happen to you? I showed to a police officer in Germany, I showed my bicycle. I bought a new bicycle. You know what was the reaction? It says, sehr schön, aber polizeiwidrig, which means not very nice, but it's against the law. And you notice there is no light, there is no belt, and for that you get arrested in Germany. Good? So you understand, you have to be very orderly. Good? Okay, guys, so now back to our current topics. You do remember expected value and how to calculate it, yes? So expected value, or before that, we speak about random variables. A random variable is a label. That's how you should think of it. Really speaking, mathematically, the expected x is the function that takes S onto S star, that takes a sample space and the outcomes in the sample space to outcomes in the set S star it's onto, right? So that's the definition formally. It's just a function from one set to another. But what is the meaning of a random variable? It's just a label, right? It just labels events. So here is an example of what can happen. Imagine that initially you have those 5 outcomes, and each outcome in this case, I just assigned it to have probability 0.2. They must add up to 1. Yes? Now, the outcome 1, 2, and 3, they are, from my point of view, the same. And they are relabeled as -1. Yes? So what happens? What's the probability I get -1? It's the probability I get 1, 2, or 3, which is altogether 0.6. Easy, right? So then what's the probability I get 0? So only one thing is relabeled as 0. Only the universe 4 is relabeled as 0. So the probability of 0 is still 0.2. And the probability of 5, it's 0.2. So since 5 was relabeled into 1, it keeps that same probability. So you see what happens. This relabeling induces S star to be a new sample space with different probabilities. But for a very, very simple reason. You can think of it as an entirely new sample space, or you can think of it as the old sample space with the outcomes relabeled. So those distinct universes are now named with the same number. Agreed? They have the same price minus 1. Easy, correct, guys? So X, random variable, is just a function from one set to another. There is nothing random about labeling. It's not a random label. The reason it's called random variable is that the outcomes of X, the labels that are actually produced, will be randomly generated because the outcomes in S come out randomly. Everyone understands? Yes? Good. Well, and then, guys, I might have, now since those are numbers, I can have a further function from set S star. I can define the function gx, and I decided to just use the example gx equals to x squared. And what is that? This is just taking those numbers and it squares them. So it's just, again, a rule that tells you how to assign, how to relabel the labels. What is that? So somebody sends me something, some screenshot of something. Anyhow, so good. So what happens then is minus 1 and 1 are in turn relabeled as 1. And you see, if I trace the labels back to the original sample space, we see that 1 is the universe is 1, 2, and 3, and the universe 5. So altogether, the probability of the label 1 coming out at the end here is 0.8. And the probability of 0 coming out is 0.2. It just only 4 was eventually labeled as 0. You see, it was labeled as 0 here, and again relabeled as 0 in S star. Okay, so such transformations from one label to another will play a major role in probability throughout the semester. And it's very important for you to understand how to manipulate this information. Now, what is the expected value of x squared? What I'm asking, what is the expected value of x squared, is then directly what happens is that I run the simulation here in S star, and I either get 0 or I get 1, right? If I play 100 games, 20 of those games roughly will be 0, and 80 of them will be 1. And I just take the average of 20 times 0 plus 80 times 1. Yes? And the average will simply be 80 over 100. So you can see that the expected value of x squared is going to be 0.8. Do you agree? It's going to be 0.8. And here we where is it? Here it is. We calculated it 0.8. Very easy. Yes. But what's going to be important, guys, is notice in this case, I spent some time tracking the labels and tracking the probabilities, right? I just neatly organized 0, 1, and the probabilities, right? But in general, I can calculate the expected value in at least 2 obvious ways, right? Because I see a table, right? So I have this. If you remember my simulations with the Wheel of Fortune, then I developed an ideal table of outcomes and the corresponding payoff, right? Or of the label X and the corresponding probabilities of getting it, right? So what can the table be? If I look at the situation, let's draw the situation into a table. Good. So let's do that. And we should see how to organize that table. So the table looks like this. So this is the outcome S. this is the probability P of S, and this is then X, and this is GX, which in this case is X squared. Yes. So we can group probabilities. We can do this by outcomes in S, right? So what happens in this ideal table? I either get outcome S1 and it has probability 0.2, or the outcome S2, which has the probability 0.2, or the outcome S3, which has the probability 0.2. S4 also has that same probability, and S5 has this probability. Yes. And then what are the corresponding values of X? The corresponding values of X are, well, I believe the first three were labeled as -1. Am I right? Let me just check. My memory is short. So yes, the first three were labeled as -1, the next as 0, and the last as 1. Yes. So what do we get? So this outcome in X corresponds to -1. This also corresponds to -1. This also corresponds to -1. And for S4, this corresponds to 0. And for S5, it corresponds to 1. Agreed? And for GX, what do we have? For GX, we have that this outcome, it's the square. So this corresponds to 1. This corresponds to 1, this to 1, this to 0, and this to 1. Yes? So how can we look at this table? We can also calculate the expected value of X squared by simply observing that this random variable, let's call it Y, right? It's Y. So we can say, well, it is Y of S1 times probability of S1. Right, I can average this way. I can average using this column, right? Because all I'm doing, you remember, guys, I hope I'm not confusing you in any way. This is just an ideal table. And if you, again, review very carefully what I did for the Wheel of Fortune, right? This ideal table is just, you see why you have to, why that would be the average, right? All you're doing is just calculating the average by grouping the terms based on either the column S or the column X or the column G. So there are, I mean, I can have 3 ways of computing that average. You agree? 3 ways that are immediately obvious. And if you are good with this, you will understand lots and lots of things. You will understand even a very difficult question. Well, maybe it's not so difficult, but the one I solved yesterday at 3:30, right? That is going to be on one of your exams because it's interesting, I think. So it's like this, plus Y S2 times the probability S2, and so on and so forth, right? And then what you get? You get what? What's the why? This one is 1 times 0.2 plus 1 times 0.2, and all the way until I reach 0 times plus 0.2 plus 1 times 0.2, and you can again see that we get 0.8. You agree? So this is calculating the average based on summation where I order the table about S, right? This is summation ordering the table about S. Now, what happens if I order the table around X? You understand what it means to order the table around X? It means I arrange the outcomes in X in order, and maybe I collapse identical columns, right? So next, I will have the same table. And I don't need the S, then I want to reorder it about X. So that means what? That means that here is X, and here I want to calculate probability X, and here is Y equal to X squared, right? The G function, right? So what values can X have? It is -1. And you see what I do, guys. When I order in X, I have -1, -1, -1. It's the same outcome. I collapse them into one row. Collapsing them into one row means adding 0.2, 0.2, 0.2. Yes. So that is 0.6. Yes, Chiara, very, very good. Ryder, very good. -1. Well, I like to keep them in order. If it's -1, then 0, then 1, right? I like my tables to be ordered, just like I like my Kafka protocols, right? And nothing is correct unless it's bureaucratically correct. You understand? And if you get that, then you are right by the law. So we have 0, and 0 is 0.2, and we have 1, and that's also 0.2. Yes. And then what is this outcome? This outcome is 1, 0, and 1. Again, what do I do now? I just have 1 times 0.6, 0 times 0.2, and 1 times 0.2. And again, I get the same exact expected value, the same average. You understand why do I get the same average? Just because I summed up the same terms, but in different orders. Right? All I did is I took the orders and I just rearranged them. And finally, of course, the one we did is we grouped, look at it here is 1 and 1. What we actually ended up doing initially, we ended up grouping by y, by g of x, right? And that means that we are listing the scores in order for g, right? And then doing the average based on that. So we can collapse the table based on the last column. That's all that is happening when you do expected values. If you really truly understand it, you will be able to manipulate expected value like you're in first grade. So easy. Okay, so this is what we just verified. That we will try to make into a theorem, which hopefully will not be too confusing, guys. Right? So here I calculated expected value directly. But I could have calculated the expected value. So that's the direct calculation, right? Look at it, 0 times that y is equal to 0, 1 times probability y equals 1, and we have this number, right? Or I could have calculated it like this: -1 squared times 0.6 plus 0 squared times 0.2 plus 1 squared times 0.2. And what is this doing, guys? This is ordering the table based on the labels in X. You understand? I have the initial labels in the sample space, 1, 2, 3, 4, 5, right? Then I have the X labels, and then I have the final labels. So I can calculate the average by grouping by either the original names of the outcomes or the modified names of the outcomes or the modified and new outcomes of this process, right? Okay, so this is what we are going to say in a proposition, which I hope is then very simple for you. If X is a discrete random variable that takes on the value xk, the value is xk with probability pxk, then for any real valued function g for which the infinite sum is less than infinity, the expected value of g of x is the summation from 1 to infinity of gxk times pxk. So what is this theorem telling you? It tells you that even if the outcomes, there are infinitely many payoffs, infinitely many entries in the table, you can take the average by grouping against the variable x. You understand? So we had some label x, and then we have a relabeling in terms of x, which we call g of x. Good. So this tells us just this is how g is determined by x. This is just how the relabeling is doing, and the summation just tells you group by x. Now the reason it's even a theorem is because it is not true for arbitrary infinite series. There are infinite series, for instance, the harmonic, alternating harmonic series, that if you rearrange it, you will get different values. You understand? It's not true that summing infinitely many terms always gives you the same value. It is true for absolutely convergent series. That's just the technical situation. Okay, so that's what I try to say in this remark is, if I have 1 minus 1/2 plus 1/3 minus 1/4, this converges to a particular number. I think it's either ln of, I believe ln of 2 or ln of minus ln of 2, one of them, right? It's easy to verify. It converges to a particular number. But if you rearrange those terms arbitrarily, you can make it go to any value. You can rearrange it to go to any number by the right rearrangement. Because if you take absolute value of 1 plus the absolute value of 1/2 plus the absolute value of 1/3, this will not be absolutely convergent. It will be a divergent harmonic series, if you remember from Calc 2. Yes? So here is the proof. You understand, guys? By definition, expected value is defined how? I mean, at least some books give the definition. To me, I see all of them as equivalent. But usually when they give a definition, they say the expected value of a random variable is the one particular value that the variable takes times the probability disappears. So one label times the probability of the label plus the next label times the probability of that next label, right? So that means you have to arrange, if you're calculating the expected value of gx, you have to arrange by the last column, by y. So the expected value of gx is supposed to be all the values that it can take, the different values it can take, times the corresponding probabilities that this value appears. Yes? So that's how the definition goes for y, right? So we have yj, let's say it takes y1, y2, y3 onwards, times the probability that we get yj. And what's the probability in terms of the previous label x? Those are all the summation of all the probabilities xk such that gxk equal to yj. You remember, guys, what it is in this situation, right? So what am I talking about? So here we have 0 and 1, only two, right? Only two labels. So it will be 0 times the probability of 0. Now, how do I trace the probability of 0 in terms of the previous variable? Well, it is it's g, or it's g of it's basically it's all the things that all the probabilities that contributed to this outcome, right? So here you see it's 0.2. Right, but what about this one, right? So this one was produced out of x1 and x3. It was this number squared and this number squared. So this number corresponds to a non-zero probability 0.6 plus this number corresponds to this probability. So what I do is I take this label and multiply by this probability plus this probability. Yes? Are you still with me, guys? It looks very technical, and it's something that might look difficult, even though it's tremendously simple. Please confirm that you follow me. Last semester, I've seen lots of people that were confused. That's why I made that simulation with the Wheel of Fortune. Yes. So the summation, all it says is, okay, is all the distinct values that y can take times the probabilities that this value appears. Now, what's the probability that this value appears? It's the summation of all the probabilities of the x k, where xk contributed to that label. In other words, xk was relabeled, was moved and was made into yj. So it basically says you take the same position of the probability in the list where y is. Yes, well, it's exactly that's what it's adding those things up. So what this is saying, in particular, let's say yj, we only two values. This is the interesting one. So how do I get? It's 1 times the probability that I get 1. How do I get this probability? It comes from all the probabilities of all the labels of x that contributed to this label. So in this case, it's -1 and 1. So it's 0.2 plus 0.6 that contributed to this label. Yes. So in general, it would be the summation, which I don't know how many terms it is that I just refer to it. So it's all the case such that gxk made the label yj. And I add the probabilities. And what is this, guys? This is just a particular infinite series. So I can push the yj inwards. And when I push it inwards, yj is equal to in the summation to any of the gxk, right? So in particular, this 1 equals to g of 1, and it's equal to g of -1. So I can just freely call it g of xk times the probability xk here, right? And then what can I do? This is the same thing. I just push the y in, and I call it in terms of the probability next to it, in terms of the term inside of the probability next to it. Good. And what is this, guys? This is now, if you look at it, just a rearrangement of this series. So this series and that series, they are adding exactly the same terms, but not in the same order. Good. So this is a sort of proof why basically this is a proof that arranging the expected value by x or arranging it by y will produce the same summation, the same average. So you don't have to do certain work. Sometimes it's best to do it this way. Sometimes it's best to do it this way. It makes a huge difference, as you will see, right? It seems like what does it matter, but how you arrange actually makes a huge deal in your ability to solve this problem. Wonderful. So let's illustrate this idea just again with one more example. Okay, so suppose that x takes the values plus minus 1, plus minus 2, all the way to plus minus n and so forth, right? Where the probability that x equals to n is the same as the probability that x equals to minus n, which is 1/2 to the absolute value of n plus 1. And what we do is we let y be the absolute value of x. So you agree that what is y doing? Y is just the numbers 1, 2, 3, 4, 5, right? So by computing the expected value in terms of y, I arrange the outcomes in y. The outcomes in y are 1, 2, 3, 4, 5. So the summation from n equal 1 to infinity of n, right? And times the probability that I get this n. Now, how can I get the positive n? Either I had the negative n or the positive n. You agree? So it's actually a sum of two terms. Here they are. That's when x is minus n, and that's where x is n. Are you with me, guys? In this case, each outcome has it's collapsing. Y is collapsing two probabilities. Maybe you should use the letter V if you understand it very well. V for verstanden, right? That means that you really understood it. Not just Y, not English type of understanding it, but really understood it. Good. All right. So you see what is this, guys? Now, what is this plus that? It's simply, this number is simply 1/2 to the power of n. Right, so that's pretty clear to see, right? It's basically because it's absolute value, they are the same. It's the same as let's say the probability that y equals to, let's say, 2. Probability that y equals to 2 is 1/2 to the power of absolute value minus 2 plus 1 plus 1/2 to the power of 2 plus 1. So it's 1/2 cubed plus 1/2 cubed, and that becomes 1/2 squared. Yes, so here we have n times 1/2 to the power of n, and you recognize this thing. I said that should remind you very much of what? It should remind you of that game. That's a Russian roulette with two chambers in this case, right? And so in this case, how many rounds does the game last? It lasts 2 rounds, or you can calculate it directly. Right, because you see, just if you have 2 chambers, it means what you have is how long does the game last? It lasts n rounds if the shot is heard on the nth round, and so you have no shot, no shot, no shot, no shot, n minus 1 no shots. It's 1/2 to the n minus 1 times 1/2, which is the shot, right? So it's that same scenario, and then even without calculation, you see, it's on average. Every 2 games I hear a shot. So on average, 2 rounds is how long the game lasts. Yes, and you know that if you watch the Deer Hunter, then of course you would just right away know that that's true. Good. Now, and then of course we can do that by the proposition. We can simply add it up directly without rearranging it. So that means the scores are negative or positive. So here I add the scores, absolute value of n when n is negative, it's this series, plus when n is positive is this series, the 2 parts. And again, what do I get? I see that this is just the same number, right? It's the same number as from 1 to infinity. So it's twice this value, and we get 2. Good. So that just illustrates that you can rearrange terms and you get the same value. Now, next is if a and b are constants, then the expected value of ax times ax plus b, sorry, it's a times the expected value of x plus b. And that follows very easily because of that proposition. Look at it. I don't want to rearrange it in terms of this variable. I will just add up ax plus b times the probability of x. You see? So I use the x column to add up the probabilities. And when I do that, I can distribute the px here and here. And that's what and break the sum. And what do you see here? This is the summation for the expected value of x. And this is b times the summation of all probabilities, which is b times 1. And we're done. You see? So this proposition is clear once you realize you can arrange by different columns. So here we have variance, the next idea. So knowing the average payoff per game is not that much information about how varied the game is. Maybe the game is very monotonous and maybe you see huge fluctuations. So here you have 3 variables. One of them is just 0 with probability 1. One of them is -1 and 1, each with probability 1/2, and the other is -100 and 100, also with probabilities 1/2 and 1/2. All of those random variables have the same expected value. It's 0, right? It's just basically 1/2 times -1 plus 1/2 times 1. So you are just canceling them out at 0. On average, it's pretty obvious. On average, you get 0. Right here, on average, you also get 0, but the game fluctuates. Here, sometimes you're broke, you lost $100, and sometimes you have extra $100. Here, you're always broke, right? So we need another measurement that might give us a sense of how interesting this game is. How much variation do we observe? And well, what are the ideas that we can have? Well, we might try to see how far away on average is the value x from the average. You understand? So I know the average. Now, how much on average is the actual outcome from the average? Does it make sense? So it would have been modeled by the expected value of absolute value x minus mu. Do you agree? X minus mu is the distance of the random variable x to the average we calculated mu. And if I run this experiment, that will give me the average quantity. Yes. Now, as it happens, this quantity is not pleasant to calculate. Absolute values are not usually easy to deal with, and it does not have certain nice properties. All right. So what we do is instead we are going to measure the square distance. You know that in calculus that when you try to find the minimal solution, sometimes you want to find the square distance, right? That because the calculations end up easier. So we do the same thing here. We take x minus mu square. On average, what is the square of the distance? Right? So you understand, if I know the average square distance, what it roughly will tell me, it will tell me roughly how. Well, I mean, I just take the square root of that and I would know more or less what's the distance to the average. That's kind of the idea, right? It's, by the way, the square root of that number, of course, is not equal to this number, but it gives you a good sense. Yes, like standard deviation, that's exactly, this is variance, and standard deviation will be the square root of it. And standard deviation is a sort of replacement to this quantity. It's not the same, but it's similar. Good, makes sense, guys. If I know the average square distance, then I kind of know the average distance. Just take the square root of that. That's kind of the idea. Okay, so how do we calculate the expected value? We can find a neat formula for the expected value of x minus mu squared. So here is how we have it. We call it, first of all, a variance. And if mu is the expected value of x, then the variance of x is the expected value of x minus mu squared. And so observe that we can square this. X minus mu squared is x squared minus 2 mu x plus mu squared. And then this is the summation, you see, where what I'm ordering the table by x, right? By definition, I should order most books define expected value as in ordering by the values of the payoffs of this variable, right? But the variable y is x squared minus 2 mu x plus mu squared, and I can order by the x. We have this. So distributing, we have this value, we have this value, and we have this value. All simple, right? Just distributing this, and it's a summation. We just group like with like. Now, what is this part? This is the expected value of x squared. What is this part? Is the expected value of x times minus 2 mu. And finally, this is mu squared times summation of probability, which is just mu squared. And what do we get? Yes, guys, are you following? I hope you are, right? It's very, very important. I just hope I'm not losing you here. It's super important. It gives you so much power if you're able to figure such things. So what do we have? This minus this plus this. This is just you see, agree, it's just this is just again mu. So we have this is expected value of x squared minus 2 mu squared plus mu squared, and they just mean together minus mu squared, which is the expected value of x squared minus the square of the expected value. That's that formula that if you took psychology, you almost were insane. I mean, just explain it to you in those methods, in their numeric methods, but without giving you a sense of what this thing is. Right? Not sure if anyone of you are a psychology major or have taken it. I almost completed a degree in psychology, but it was very, very annoying to me, especially that they use statistics and they did not know nothing about it, right? Good. Good. So we have this calculation, and let's now actually test it out, guys. So first, let's calculate the expected value and variance for the outcome on a fair die. So we know the expected value is just the summation from 1 to 6 of k over 6, and the result is 7 over 2. You agreed? The result is 7 over 2. I hope you know how to calculate it. Now I'm going to wait, and you are going to calculate the variance. Variance of the die, of the outcome on the die. Well, for some reason I'm seeing 3.5 times 1 over 6 squared and whatnot, and that's not right. Right? The expected value x squared, that is what you are considering. What is x squared? X squared. So x squared is 1 squared, 2 squared, 3 squared, and whatnot. And when you're looking at this this expression, it's just 3.5 squared once, without multiplying it by any probabilities. Thank you, Barry. Okay. let's see, guys. So the variance is what? So summation of k squared over 6. I'm calculating expected value of x squared. What do we get? You know how to sum x squared, how to sum k squared, correct? It's 1 squared plus 2 squared plus 3 squared. The formula you should know combinatorially. By the way, there's a nice way to do it combinatorially. And that would be what? It will be 6 times 7 times twice 6 plus 1, which is 13, divided by 6. Right? That's where the 6 comes from. So altogether, what do we get? We get 91 over 6. And then when we calculate variance, we just from it, we subtract 7 over 2 squared. And when we simplify, we get 35 over 12. Good. Now, here is a useful observation regarding variance. We know that variance of ax plus b is simply a squared times variance of x. That's almost clear because, I mean, what happens? What's the expected value? If I have ax plus b, the expected value is simply a times mu plus b, if mu is the expected value of the original variable. Yes, so that's the new center. So the expected value of the new variable minus the new center here is what? The b's are just eliminated, so it doesn't influence the variance. And so what do we have here? We have a here, right? So we have ax minus a mu squared. And so when I factor out the a, I get a squared. And we know that I can move constants out of expected value, right? Expected value of anything times the same property here, right? I just expected value is linear in that sense, right? We're going to see that expected value is a linear map. If you study linear algebra, you know what I mean. Good. And that just gives us a squared variance x. Okay, I think we're here. Now, properties of expected value. This is going to be an interesting lecture, I hope. Okay, now again, guys, we mentioned that I can calculate the expected value of x by adding things, by grouping by the sample space S, right? So it's a summation of the label at S1 times the probability plus label at S2 times the probability, and so on and so forth, right? And similarly, I can also calculate the expected value of g of x by working with the original sample space. This is just a label on the elements of the sample space, right? So this element is gxs1, and this element is gx2, and onwards. Good. And this is a majorly important theorem, guys. That's why what you can observe if you do the summation based on the original sample space. Here is the theorem. If x and y are any random variables over the same sample space S, the expected value of x plus y is the expected value of x plus expected value of y. In other words, expected value is additive. You see, you can factor out a scalar and it's additive, so it's a linear map in that sense. If it were a vector space, it would be a linear map. The reason you don't usually hear it is because sample spaces are not always linear maps, but it behaves like a linear map. So what do we see here? Well, z is x plus y. Let's label it this way. What's the expected value of z? If I calculate it by grouping on the column where the original sample space outcomes are listed, it's just going to be summation of zs times ps, which is summation of xs plus ys times ps. And then I can distribute the ps and distribute the summation. You see what we have here? And here is the expected value summation for x, and this is the expected value summation of y. And of course, we can extend it to any number of outcomes. It's the same exact situation. Yes. So the expected value of x1 plus x2 plus all the way to xn is the sum of those expected values. And let's see if we can understand what happens here. Suppose now that I'm going to throw two fair dice. and I want you to calculate the expected sum. In other words, on average, what sum on the two dice will come? Think of it and I'll be back. Radar, unfortunately, I don't understand for B, for what B? Don't do B, do A. Well, yeah, now I see what you mean. Yes, I see. That's good. That's good. All right, guys. So what's the situation? So you see, you could calculate this expected value in two ways, and you can see that one will be very difficult and the other would be very easy, right? What is the difficult way that most people, if you're not careful, most people pursue this alley? So they would say, okay, summation, right? So they define the variable z, and that's the summation, and z can equal to what? It equals to 2, 3, 4, all the way to 12, right? So then what do? Then you can say that the expected value of z is the summation where you have n equal to 2 all the way to 12, and then you have n multiplied by the probability that z equals to n. Yes? Now, do you remember what's the probability that z equals to n? Right? So the probability z equals to n is we can calculate it, right? So if the summation is equal to n, that means the first variable, which is x, z is x plus y, right, is between so we have here x plus y equal to n. Here we have x is bigger than 1, less than 6, and y is bigger than 1, less than 6. So what do we have? We see that if x is equal to k, if x equals to k, y has to equal to n minus k, yes? And then we need to know what is the possibility for k. So n minus k has to be between 6 and 1. And that means that if I move things around, that means that k is bigger than or equal to 6 minus n, and less than or equal to 1 minus. So to 1 minus n. Right? Right? Not. I mean, the other way around. Apologies. Yes, it means 6 n minus 6 and n minus 1. Yes. You know, I'm just doing the inequality. So I want to see what is the inequality for k. And I simultaneously know that k has to be less than or equal to 6 and bigger than or equal to 1. And so how many k's are possible? So k is between the minimum, the maximum of 1 and n minus 6, and minimum of n minus 1 and 6. Yes, that's basically what I did here, guys. You can just repeat it. I just for an arbitrary n calculated the number of outcomes, right? So if the outcome is the sum is 3, how many possible die combinations give you 3? If it's 4, then how many die combinations give you 4? Yes. So you see how tedious this process is. I I understand this probability, and then from there I have summation n equal to 2 until 12 of n times minimum n minus 1 6 minus maximum. I don't even want to write it, it's a bit long, and we need to add 1 divided by 36. So I am not done at all if I do it directly, right? Look how much time I waste if I did not realize that I can do this problem so much easier. This I just calculate the probabilities, I assembled, calculate the probabilities, and I still have to sum. Now, on the other hand, what happens if I just go directly and do that? Well, I realize that the summation is the value of x and the value of y. And what is this? So that's the expected value of X plus the expected value of Y. And since they are identical dies, it's symmetric. Barry, but we're not doing 2 plus 3 plus 12 over 36. We are doing the number of combinations that, because that's not the probability. It's 2 multiplied by the probability of getting 2. So it's 2 multiplied by 1 over 36. 3, how many ways to get 3? 3 can be gotten as 1 and 2 and 2 and 1, 2 ways, right? So 3 times 2 over 36. How many ways to get 4, right? So it's from 1 to 3. You can see, so there are 3 ways to get 4. So it's 4 times 3 over 36 and onwards, right? And you have to do it for 12 of them. So it is doable, but not already much slower than this process. And in many cases, you would be really stuck against a hard wall if you do this type of way, right? Look how much quicker this one is. It's the expected value of X plus expected value of Y. That's 2 times expected value of X, which is 2, times this summation, which is 2 times 7 over 2, which is 7. So right away know that the average is 7, and I wasted very little time with it. And imagine doing this. You see, if you found this not so problematic, imagine having to sum to figure out the expected value on 12 dice or 100 dice, right? So, or in general, n dice. Can you imagine how many combinations there could be to produce this, to produce any particular probability? But the average can be calculated by just sample over the sample space, right, over S, and that's the expected value of x1 all the way to xn. Yes, and that simply is n times 7 over 2, right? So I can create tremendous simplifications by regrouping by the sample space. Yes, so it's n times 7 over 2. Here is another example, guys. We're going to do this one several ways just to illustrate all combinatorial processes. We have an experiment, and it consists of n independent trials, and each trial is success with some probability p. What's the expected number of successes in terms of n and p? In other words, if you throw a coin, for instance, right, you take a coin, the probability of a coin is 1/2. How many heads do you think you will get if you throw it 10 times? Yes, on average. With coin, it's pretty obvious, but in general, if the coin is loaded, or maybe it's a loaded die or something, and the success rate is with probability p, how many successes do you expect to see if you run n trials? Very good, right there. And of course, justify. Don't have to justify by comments, but can you justify? Yes, how do you explain it? Well, let me try, guys. Let's do a few of them. So here are several explanations. So one of them we can think intuitively. Okay, we think of probability as a limit, right? So what is that p? How do we obtain p as a limit? Well, we perform infinitely many trials, and what we do, we take number of success over total number of trials. You agree? So p will be obtained as m successes divided by m total trials, right? Now, what happens if I group that experiment by packages of size n, right? If I group it by packages of size n, that means what? That means that that in the total number of outcomes that I will have, if it's packages of size n, I will have n times m outcomes. Do you agree? Maybe I should write it anew, just to be clear there. How will I do that? You see, guys, you all agree that P is equal, by this frequentist interpretation, limit as m goes to infinity of m success divided by m, right? Now, I am not interested in just, I don't want to group by one trial. I want to have n trials in total. A bunch of n trials means what? So P would also be equal to limit as m goes to infinity of n well, if I have, let's say, let me see how to do that. If I have n m, right, n m trials, then this is I'll consider it as n m success. What does it mean? That means out of n multiplied by n, so that we have them in packages of n, how many of them were successfully created, right? Now, that's also so the number of, if I now multiply, you see, so here actually I don't want to divide by nm. Do you agree? Because I actually, for respect to my experiment, I performed m experiments where in each I have n trials. Yes. So what do? I multiply it by n. I multiply both sides by n, and I have n times p is equal to limit where m goes to infinity. Altogether, we had n m attempts, and of them, that I take it as a one simple, right? Of them, we have a bunch of successes divided by m trials. You understand what I did, guys? I mean, maybe the symbol nm throws you off. I might have to come up with a better one, but the idea is this. What I do is, if I perform infinitely many trials, I take the ratio of successes over all the trials, I get p, right? But my actual experiment consists of batches of size m, so of size n. So what do? I perform one series of n trials, then two series of n trials, and onwards, right? So what do I divide? So altogether, how many experiments did I perform? I perform nm experiments. Of them, nm parentheses, that's how many successes I have of them, right? That's successes per nm individual experiments. But I don't divide by nm, I divide by m, because with my point of view, I performed only m full experiments, because each experiment is a batch of n. Are you following? So the answer then easily is n times m. Don't worry, if it's still confusing, I will do it in another way. Right, so we have this. Next, you can try to understand it. Next is the easy way. So the easy way is I'm going to define indicator variables. So xk will be 1 if the k outcome is a success. You see, what is my sample space? My sample space is a string of zeros and ones. So how many of them? There are 2 to the power of n possible possible outputs, right? Because you have 0 or 1, that means first success or failure, second success or failure. So 0, 1, 0, 1, 0, 1, it's 2 to the power of n size of the sample space. So it's n strings. and I have the variable xk just looks at the kth input in that string, and if that input is 1, then we add it, right? So how many successes we have? We just add x1 plus all the way to xn. So when I run the string, each of them will just deal with a particular part of the string. And still what happens, guys, the expected value of the sum is the sum of the expected values. And it's very easy to see that the expected value of x1 is 1 times p. Right, so all of them, they all have the same expected value. There is nothing special about any position in this experiment, right? The expected value of xk is the same as the expected value of x1. So this is n times the expected value of x1. Now, what's the expected value of x1? That first is either 1, it's 1 with probability p. I can ignore the others, it's independent, right? Whatever others are doing, it doesn't matter. It's 1 times the probability, times all the probabilities of anything else is happening. So it's probability 1 multiplied by 1 plus probability of 0 multiplied by 0. Now, that is what? That is p multiplied by 1 plus 0 multiplied by 1 minus p. So the expected value is p. So it's n times p. Good? We have maybe a bit more time for another question. So a new drug is tested. Out of 10 men and 10 women volunteers, a sample of 10 people is randomly chosen to participate in the trials. What is the expected number of men in the sample? Make sense what I'm asking, guys? How many men will be in the sample? We have 10 men, 10 women, 10 people are selected out of them randomly. How many men do you think are in the sample? All right. I see lots of people are messaging. So there is symmetry in this problem. And you might guess the answer is 5. But again, guys, well, symmetry. What if I gave you a not symmetric question, right? What would you do? So one solution is intuitively induced by symmetry. In this case, it's nice. you can see that there should not be a bias towards men or women. So the expected value should be 1/2 since we have the same sample sizes, right? If sample sizes are not the same, there would be bias towards the bigger sample size, obviously, right? In the average. Right, in other words, more people of one type, and that will influence this probability, right? The other way to do it, B, is to calculate expected value directly. So X is the number of men in the sample, and so we have X is either 0 or all the way to 10, and we add up the number of men times the probability we had that number, right? So if we have K men, then those are any of the 10 choose K men, and then the rest is 10 choose 10 minus K women. And the probability that I choose somebody is, the total sample space is 20 choose 10. It's just any grouping of 20 people. Yes? So you see what I do here, and then look at this red box and look at that red box. It's not, it's instructive still, those ideas are useful. Even though I used all sorts of probability things in one of the questions I solved yesterday, even that came out, you know, several combinatorial things come out. So it's still worth watching it. What is this, guys? This is equal to that. Do you see that? K times 10 choose K is the same as 10 and times 9 choose K minus 1. Right? That's because, well, we have, let's say we select a team and we select a captain for the team. Right? So first we might select the team and then the captain, or first select the captain and adjoin to him the remaining members of the team. And this I do so that I don't have K, so that my summation is easier. You see this? Right, so that we have this situation then, and then I just change the bounds of summation. I decided to say J is equal to 10 minus K, and then I get the situation, right? I get 10 choose J, 9 choose 9 minus J, and what do I see here? I see that this is equal to 10 times 19 choose 9. Right? Why? Because what is this saying? This is all the possibilities of picking 9 people out of 19. Right? And just it breaks it into how many people of one category, how many people of another category. So it's this identity here. And then what do we see here? Now here, I want to use this identity again. So what do? I factor 1/2 and I have 20. And then 20 times this number is the same as 10 times 20 choose 10. You agree? So this is again the captain thing. So this is choosing the captain and joining the team. So I wanted first choosing the team and then the captain. So this way, and why? Because then I can cross 20 and 10, 20 choose 10, I cross it out, and I have the answer is 5. You see, it involved going through several combinatorics and actually combinatorial properties, and one time we used the same combinatorial identity in both directions. Good. Now you can solve these questions with so much greater ease by doing what? By using indicator random variables. Yes. So we have we just see how many men we have. We can have all the way up to 10 men, and xk will be giving us +1 if the kth person is if I have the kth person in the sample, the kth man in the sample, right? So then what's the expected value? It's the sum of the expected values, and naturally the expected value for each of them, there is no bias, it's the same. Right, so it's 10 times the expected value of x1. Now, what's the expected value of x1? What's the likelihood that I see person 1 in my sample of 10? Well, I can see in the sample of 10, I can see what are we saying? So it's 10 over 20. Right, so it's 10 over 20 because basically for person 1 in the sample, I can actually see anyone in the sample, right? So how should I say that better, right? So if person one is in this is in the sample, maybe you also can use it's 19 choose it's also 19 choose 9. That means he is in the sample, divided by in general 20 choose 10, and you will get 10 divided by 20, same thing. You understand? Basically, just to be sure, what you see, if person one is in the sample, I picked one of samples where person one is located. How many such samples are there? 19 choose 9. You agree? 19 choose 9 is how many ways to take person one and adjoin to him the other committee, and that's out of 20 choose 10. So it's not written here. That's why I wanted to emphasize. Yes. And then when you simplify it, you still get 5. Good. I hope, guys, you are following, and I hope it's exciting. We can solve so many wonderful questions using this idea. And but for now, you are released to have a good weekend. If you want to see what happens to bad children, it excites me. Right. Can you say this? That's what Germans write for children. Yes. So they were misbehaving. So what they did with them, they put them into the grinder, and that's it. And nobody felt sorry. Take care.
Professor?
Yes.
Can you hear me?
I hear you.
I was wondering if you sent the running grade to my high school counselor.
No, of course I have.
Oh, you have? Okay.
A while ago.
Okay, just checking in. Because
Okay.
she's like, right now she's the most important person in my life, you know, so.
Why is that?
Because I'm applying to colleges now, so he's my college.
Okay, don't worry, you'll do fine.
Okay.
Yes,
Right.
try not to be too, how do you say, just learn and enjoy it, and try. You see, people when they're young, they always are just trying to get somewhere. Make sure where you go is where you want to be, right? You don't want to be a workhorse or tortured or anything. You just want to. You're doing very well. You're understanding stuff, and sometimes for many people, at least for me, what I need is for people to leave me alone. Then I can do a lot. Right. So let's say Harvard and things like that, I would not enjoy it at all. Right. I would not ever want to go to MIT or Harvard or any places where they make me do stuff. Right. Just my personal observation. Right.
Yeah. The college counselors do talk a lot about like fit, which is essentially how well you think you'll be able to succeed in the environment of the college. So like I am keeping that.
No, you might be very successful and you might enjoy it, but I can tell you that some people, and many of them, even if they do it very well, they at some point think, why did I do that to myself, right? My brother, for instance, went to such things, and he ended up hating everything related to academia.
Oh boy.
Yes. As like, you're doing very well, and don't let anyone take it away from you. Like, I think you can do a lot of great things, right? So at the age, you're learning stuff. So that's all I'm thinking about, right? So I think you'll do well, and the most important thing is just self-study. I think if it's mathematics, there's the only thing about colleges is connection. Is that you might go to Harvard, it's very impressive, and the connection is then people are like, oh, you're from there, and they give you a good job right away. But aside from that, aside from connection, I do not believe that it gives much. I think it takes much.
All right, I will think about that.
Yeah, I don't think you will, but just in case.
Oh man. No, I get it. Like for example, like Princeton, it's like that place is very academic, very crazy. So I
Yes.
don't think that I would want to spend like 4 years there. So
Yes, what you want is, let's say, I can tell you what I did in college. I enjoyed my time, did virtually nothing, and chased girls, right? And
okay.
I learned to run faster.
Okay.
Okay,
All right.
take care.
I probably won't do the same, but
Why
you know,
not? Okay, but do whatever you like.
maybe I will. Maybe I will. Who knows? Okay. All right. Thanks, Professor. See you.
Bye.
Bye.